Hey guys, welcome to another Further Pure 1 revision video. Today we're taking a look at the T-Formula, sometimes known as the half-angle substitutions and whatever other name you want to give it. But chapter 5 from this Further Pure 1 textbook. So this is a new introduction to the A-level further maths specification. It's quite a decent topic, but you need to be confident with trigonometry and being able to manipulate trig expressions. So it's a very common theme amongst these questions, which you can see straight away from this first question here, where we're proving this identity. So what we've got here is we're using the substitution t equals tan theta over 2. We want to prove that sine theta plus sine theta cot squared theta is equal, or identical I should say, to cosec theta. So 4 marks for this. Let's have a go at it. So what I always do with these questions myself is I identify what functions we've got. So we've got sine theta, so let's write down our substitution for sine theta. So you can learn, so this should be, sine theta is fine. What you can do is you can derive it in the exam, but what I would just recommend is you learn the substitutions. Rather than having to sit in the exam and derive them, just memorise them. They're really not too bad. Sine theta is quite nice and easy, so it's just 2t divided by 1 plus t squared. Now this is the good thing, this 1 plus t squared. This allows us to work out the others a lot easier. We also have tan theta. So similar, it's 2t, but instead of being 1 plus t squared, it's 1 minus t squared. Okay, so then we have two identities for this one. And the reason why we've got tan theta is because we've got cot squared theta. So that's going to be a 1 over tan squared theta. Okay, so we can deal with that in a moment. So here now, what I'm going to do is I'm going to set up what we've got. So we've got sine theta plus sine theta times cot squared. So let's do that. So that's going to be 2t over 1 plus t squared plus, again, 2t over 1 plus t squared times by 1 over tan squared theta. So it'd be 1 over this, so that'd be the reciprocal of this, and square each one. So that's going to be, if we're doing a bracket in full, it's going to be 1 minus t squared on top, which we're going to square. And then we're also going to have 2t squared on the denominator, so that's 4t squared. Okay, we'll deal with that one straight away. So here now, what I can do is I can start simplifying this denominator and this numerator here for this product. So this bit will remain the same. 2t divided by 4t squared. Well, what would that leave me with? Well, that's just going to actually leave me with 1 on the numerator and 2t in the denominator. I'll get 1 minus t squared squared in the numerator, and then we're going to times it by 1 plus t squared. So in total, what that's going to look like is 1 minus t squared all squared divided by 2t times 1 plus t squared, like so. And then at this stage here, we want to just start simplifying. So to do that, one nice way to do it would be to get it over a common denominator. So nice and easy, to get a common denominator here, I just need to times this expression by 2t. Okay, so this left-hand fraction here by 2t. So, timesing that by 2t, we get 2t times 2t in the numerator, so I get 4t squared. We just add on this expression here, and then we divide it all by the same thing here. Like so. So here now, I think the easiest way to deal with this would be to expand this in the numerator and start collecting like terms. So what am I going to have? I'm going to have 4t squared plus, I'm going to get 1, I'm going to get minus 2t squared, I'm going to get plus t to the 4. So all I'm doing is expanding this expression here and then adding the 4t squared at the beginning. Denominator will be the same, so 2t times 1 plus t squared. And then in the numerator here, we can simplify and collect like terms. So I'm going to get t to the 4 plus 2t squared plus 1 divided by 2t 1 plus t squared. And now what we want is we want cosec theta. So that's 1 over sine theta, which would be the reciprocal of this. That's what we should expect to get. So what we want to finish with is 1 plus t squared divided by 2t. Okay, because we want 1 over sine theta. So we want the reciprocal of this. So one way that this might happen quite nicely, and what we do actually find is it does work using this, is if we factorise here and we cancel some terms. So this here, this is just 1 plus t squared. If you notice, we can factorise this as 1 plus t squared divided by 2t times 1 plus t squared. So what I get here now when I cancel is 1 over sine theta, I get 1 plus t squared over 2t, because one of them in the numerator cancels with one in the denominator. I just get one of them in the numerator divided by 2t. And like I said before, this is the reciprocal of 1 over sine theta. And 1 over sine theta is cosec theta. So therefore, 1 over sine theta is identical to cosec theta. So therefore, we've proven the identity there. Okay, so as you can see here, trig identities and just being confident with your trig functions does play quite a big part. And again, this is proven in the next question here now. So that's the first question of exercise 5b. Hopefully not too tricky. The next question here is a context question. So I think the actual term is modelling. And as you can see, the context is essentially this particle that we've got. So we're looking at the displacement of the particle, and we're given the equation for that. So that's S equals 10 minus 5 sine x minus 12 cos x. Okay, between 0 and 2 pi. So the first part just asks us to show that ds by dx is 1 over 1 plus t squared times 5t squared plus 24t minus 5. Now, I personally think the marks are the wrong way around for this question. I think the 6 marks would be better for part B, because the part A is quite short in comparison to part B, but that's how Edexcel and Pearson decided then. That's on them. But let's have a go at it. So the first thing we'll do here is we want ds by dx. So let's just differentiate this, see what we get. So ds by dx. So differentiating this should hopefully be quite standard. The 10 will just disappear. Minus 5 sine x, well, this will be minus 5 cos x. And if you differentiate cos, you normally get minus sine, so this is minus 12 lots of minus sine x, giving us plus 12 sine x. So far, pretty standard, nothing crazy. So we know what functions we're going to be using for the T-formula here. So we've got sine x and cos x. So let's just write them down. So sine x, again, that's 2t over 1 plus t squared. Cos x is really easy to remember. And how do we know cos x? Dead easy. Well, the denominator is the exact same as sine x, so it's 1 plus t squared. And then the numerator is just the conjugate, so it's 1 minus t squared. So nice and easy. So we don't have any tan or anything else, we just need sine and cos. So now that we've got that, all we need to do is use our substitutions here, replacing them here. So minus 5 lots of cos x, 1 plus t squared, plus 12 lots here of 2t over 1 plus t squared. Okay, and what we should hopefully find here is when we simplify all this in a moment, we should get what we're asked for in part A. Well, the thing I noticed straight away is this is a 1 plus t squared denominator here, 1 plus t squared denominator here. So if I just expand across here, so 12 times 2t and then minus 5 times 1 minus t squared, we've already got it over a common denominator. So what that's going to give us is minus 5. So minus 5 times 1 is minus 5. Minus 5 times minus t squared. That'll give us plus 5t squared. And then I'm going to get plus 24t. And if you notice straight away, this is looking pretty good. We've already got that in part A here. And this is all going to be divided by 1 plus t squared. Common denominator between these two. And then all I need to do here is pull out the 1 over 1 plus t squared at the front. So it's going to look like this. So 1 over 1 plus t squared. And then we times it by this bracket here. So 5t squared plus 24t minus 5. Like so. So there we go. We've got it exactly as part A as required. So that's part A done. Part B is a hence find. So if you see hence in the question, we're going to use the previous part to help us. So the first thing I can do here is use the derivative. So if we want the part where the displacement is minimised, the value of x for which this is minimised, the first thing to know is that this must be when the derivative is equal to 0. So for part B here, we need ds by dx equals 0. So in other words, what we're saying is that 1 over 1 plus t squared times 5t squared plus 24t minus 5 is equal to 0. That's what we're saying. So straight away, if I time through by this denominator, this 1 plus t squared, that will just disappear, because anything times by 0 is 0. So what we're saying is 5t squared plus 24t minus 5 is equal to 0. So when you see a quadratic like this is very common. The first thing you should try and think about is whether we can factorise it. Now, I'll warn you, it doesn't always work. You can't always factorise it. So you either have to use the quadratic formula or complete the square. But for this one, you will find that it does actually factorise. So what we get is 5t minus 1 and t plus 5 equals 0. So now that we've got 5t minus 1 equals 0 and t plus 5 equals 0, we can obtain two values for t. So simply, t is either a fifth or t is equal to minus 5 here. Okay, so we've got our two t values. But we need to consider this now. We've got two t values, but only one will be when it's minimised. Okay, now to find which one is the one where it's minimised, we require the second derivative. So let's just clear all this for now and then consider this. So we require the second derivative here. So if we just differentiate ds by dx again, d squared x by dx squared. So the second derivative here, that's just simply going to be 5 sine x plus 12 cos x. So we had t equals a fifth, and was it t equals minus 5? Let's just double check that. Am I working? So yeah, so t equals minus 5. Now, if you look here at our 5 sine x plus 12 cos x, what we need to do is we've got this in terms of t here. We've got 2 points for t. So if we use our substitution again, our half angle formulas, in terms of the second derivative, and then substitute either of these in, we'll know which one's which. So this is 5 over 2t over 1 plus t squared. This is plus 12 over 1 minus t squared over 1 plus t squared. Okay, simplifying this now, this is going to be 10t minus, sorry, that should be plus 12 minus 12t squared. And this is all over 1 plus t squared. So all you need to do here is consider one of the points. Now, looking at this expression we've got here, I look at this and I spot them. If t is minus 5, this surely won't give me a positive solution. Remember, if the second derivative is positive, then that value is for a minimum point. So the fact that this t minus 5 here suggests to me that that will not be a minimizer. So if we say t is equal to a fifth, substituting that in then, plugging it into here, that's going to be equal to 13.52 divided by 1.04, which is greater than 0. So therefore, when t is equal to a fifth, is for minimum point. Okay, so that's just one thing we need to show that's actually the minimum point there. So we know which value it works for, t equals a fifth. So now we can use our substitution here, t equals tan x over 2. So what we're saying is tan x over 2 is equal to a fifth. And now from here on out, pretty standard trigonometry, just solving this trig equation here. So x over 2 is going to be arctan, or tan inverse, whichever you prefer to write, of a fifth. So the actual final solution will be 2 lots of this. And obviously we just need to be careful about the region, but it's quite a nice one, a nice question here. So that would be 0.197. Again, make sure you're working in radians because we're between 0 and 2 pi. 0.197 radians. So x is just 2 times this. So that's 2 times 0.197, giving us 0.395. And that's simply the only solution we have for that one. Obviously due to the periodicity of tangent and such, but you don't need to worry too much about that. So we just get that one solution there, 0.395. So that's quite a long question, 9 marks in total. Like I said, I definitely think the marks are kind of the wrong way around for that, but there you go. So that brings to the end of that one. Next question, nice short one. This is often quite a nice way to start a paper. Show without use of a calculator that cot x is equal to minus 119 divided by 120. So the first bit of information is we're told sine x over 2 is equal to 12 over 13. So the question is, how do we go from this to cot x? Well, the first thing I'd think about here, and again, like I said, it's a common theme throughout this whole chapter, is your trig identities. If I can get a hold of cos here, then we can work out tan x over 2 being sine x over 2 divided by cos x over 2. And then once we've got tan, we can work out cot as being 1 over tan x over 2. So if we do that, how would we do that? Well, remember, sine x over 2 squared plus cos x over 2 squared is equal or identical to 1. Okay, so just rearranging this formula now, I can work out cos x over 2 here. So therefore, cos x over 2, what will that be? Well, that'll simply just be the square root of 1 minus sine x over 2 squared. Okay, just by subtracting sine x over 2 squared off both sides and then just taking the square root. So we can use that now. Cos x over 2, well, that's going to be equal to the square root of 1 minus, we know sine x over 2 is 12 over 13, so we just square that. Like so. Plug this in on your calculator, and what do we get? Well, we get 5 over 13. I mean, we're actually not supposed to use a calculator, so you should just do this by hand, it's not too bad. So you get 5 over 13 just by squaring that. So you get 144 over 169. So write that as 169 over 169 minus that. So you're going to get 25 over 169 and then just square root it to get 5 over 13. So I'm being a bit lazy by telling you to use a calculator. You can essentially use a calculator for this point here, just to show that you get this point here. All it's asking is that you don't use it from sine x over 2 just to get that. So the kind of preliminary work in between, I don't think it's an issue. So now we've got cos x over 2. Now we can identify what tan x over 2 is. Because that's going to be sine x over 2 divided by cos x over 2. Which in our case is going to be, what's sine x over 2? That's 12 over 13. Divided by 5 over 13. So what does that get? What does that give us? That's just going to give us 12 divided by 5. The 13 is technically just cancelled here. So we get 12 over 5 is equal to t here. So, because obviously tan x over 2 is equal to t, so therefore cot x So don't forget, this is the reciprocal of tan x. So tan x, your substitution for that is 2t over 1 minus t squared. So 1 over that is 1 minus t squared over 2t. So all we've got to do now is use our t value here, which is 12 over 5. So this is 1 minus 12 over 5 squared divided by 2 lots of 12 over 5. So work this out here. What you should get in the numerator is minus, I'm going to run out of room. Let's do it up here. That's minus 119 divided by 25. Divided by this denominator here is 24 over 5. And if you work this out here, what you get is minus 119 divided by 120 as required. So I know I'm squishing it a little bit at the bottom here, but I hope that's kind of illustrated the point there. So again, be confident with your trig identities. If you struggle with trig identities, go back to your A-level maths, practice it, make sure you're confident with it, and then come back to this. You'll find this chapter much easier with that prior knowledge. So now let's move on to the last two questions, and the last two questions I've picked from the exam papers that we have available. So that's the June 2018 exam, this is the AS exam, and we also have the sample assessment exam. So these questions are very standard. This question here, we're going to show that this equation can be written in the form 7t squared minus 5t minus 5, and then we're going to solve it. So let's have a go with it. So the first thing to note here is what trig functions we're working with. Well, straight away, shouldn't be too difficult to spot. We've got sin x and cos x. So sin x, that is 2t over 1 plus t squared. And then cos x, remember, same denominator, but different numerator. 1 plus t squared, and then it's just a conjugate, so 1 minus t squared. So that's a nice, easy way to remember it. So now, all I need to do is use my equation, 5 sin x plus 12 cos x equals 2, and then replace it with our t formula here. So that's going to be 5 lots of 2t over 1 plus t squared plus 12 lots of this here, so 1 minus t squared over 1 plus t squared. And this is equal to 2. So like you can see, these questions are usually written to where, I mean, not always, but to where the simplification is quite nice. Obviously, the intended effect isn't to where simplifying the equation is ridiculous, because the idea is to demonstrate that you actually understand how to use the substitutions and the formula rather than just getting stuck on some tricky simplification. So the fact that we always get a common denominator is quite a good sign. So if we simplify this here now, again, over a common denominator, so I just need to multiply across and then add together. So 5 times 2t gives me 10t plus 12 minus 12t squared. And that's over 1 plus t squared. And that's actually equal to 2 at this point. Now you can subtract the 2 off and make it equal to 0. What I'm actually going to do is I'm just going to times through by 1 plus t squared. So what would that give us? So I still get my 10t plus 12 minus 12t squared. This is equal to 2 plus 2t squared. Okay. And now at this stage here, notice it's the 7t squared is positive. So what I'm going to do is add 12t squared onto both sides and get these t squareds in terms of being positive. So everything needs to go onto this side. So if you basically get rid of this side and make it equal to 0, I need to add 12t squared minus 12 and minus 10t. So what would that give me? It'll give me 14t squared. It'll give me minus 10t, and it will give me minus, no, what am I doing? Minus 10. I can't do basic maths. And this is equal to 0, right? So that's good so far. And then just to finish it, hopefully it's not too difficult to spot. All we need to do is divide through by 2. So dividing through by 2, we just get 7t squared minus 5t minus 5 equals 0 there. And that gives us the expression we need as required. And then part B, we're going to use that equation that we've just got, this 7t squared, this quadratic here, to solve the equation. So let's have a go at that. So if we clear all this just so we've got enough room, shouldn't be too tricky. So like we always say, have a go first at factorising this. So can we factorise 7t squared minus 5t minus 5? Well, the unfortunate thing with this one is we can't factorise it. The good news is we get a bit of practice with a different method. So you can complete the square or use the quadratic formula. The method I'm going to apply for this one is the quadratic formula. So what I'm saying is that t is equal to minus b, so that's minus minus 5, so we get 5, plus or minus, so again this shouldn't be too bad, this is just kind of your GCSE maths, 25 minus 4 times 7 times minus 5. So don't forget, I'm just doing it for this quadratic here. This is all divided by 2a, where a is 7, so divided by 14. And if you simplify this, what you should get is 5 plus or minus square root of 165 divided by 14. So what we get here is two values for t. We get one when it's 5 plus root 165 divided by 14, and then 5 minus this expression here. So what we'll do is we'll work out each one individually. Really what you should do is you should take tan inverse of this full expression. I've been lazy and I've took it to a reasonable amount of accuracy. So what I did is I worked out each one individually. So t is equal to 1.274659, and t is also equal to minus 0.560374. Okay, and now all I need to do is take tan inverse of both of these. So don't forget it's x over 2. So our substitution is t equals tan x over 2. So x over 2 is equal to tan inverse. So if we do this one first, 4659. And again, these should really be just kind of standard, trig equations. So I get x over 2 is equal, so we're working in degrees this time, so just be careful for that, 51.88498, so on. And now if you times this by 2, you get 103.8 to one decimal place. Okay, so that's one solution. And then my next solution is for this t value here. So x over 2 is equal to tan inverse of minus 0.560374. So x over 2 is equal to minus 29.265125, so on. And we can times this by 2. And obviously the good thing is both of these solutions are obviously between your range here. So between minus 180 to 180. Obviously that's just something you need to be careful of. But with it being the first question, we shouldn't expect anything too crazy. So times this by 2, we get minus 58.5 degrees there. And again, to one decimal place. So that brings us to the end of that one. So we get two solutions there. So x is 103.8 and minus 58.5. And then for the very final question here, another question where we're looking to basically use the identities and use our formulas to get a required result. So the first question is sec x minus tan x. We want to show that it's identical to 1 minus t divided by 1 plus t. So the first thing I'd do for this question is I'd write down the formulas that we're going to be using. So sec x, that's 1 over cos x, and we have tan x. So if we write down cos x and tan x, so cos x, remember, it's 1 minus t squared divided by 1 plus t squared, and tan x here, what would that give us? That would give us 2t over 1 plus t squared. So, oh, sorry, I made a mistake. That's 1 minus t squared. I'm getting carried away. 1 minus t squared. Right. So we've got the first bit right, just about. Now we can use our formula. So, sec x is 1 over cos x minus tan x. So using that information, what's that going to be? Well, that's going to be 1 over this. So let's just write it out in full. 1 over 1 minus t squared over 1 plus t squared minus tan x, which is 2t for 1 minus t squared. So this here, the 1 plus t squared will come on top. You times it by 1 and just keep the same denominator. So what we're going to get is 1 plus t squared over 1 minus t squared minus 2t over 1 minus 2t. Okay, so at this stage, everything looks good. I can't spot any mistakes. Apart from the fact that I'm writing 2t. What am I doing? Right, okay, I'm having a nightmare now at the end of this video. So this is thankfully the last question. 1 minus t squared. Right, so we've got it over a common denominator here. We can just keep this now as one numerator. So this is t squared minus 2t plus 1 divided by 1 minus t squared. Right, there we go. So now, what I want to look to do here is factorise. Given that the final bit we end up with is 1 minus t over 1 plus t, the first thing I know is that this is the difference of two squares here in the denominator. So, do it up here. 1 minus t squared, well, that's equal to 1 minus t times 1 plus t. If I have a 1 plus t in the denominator, what I expect is about 1 minus t cancels with a 1 minus t in the numerator. And how does that work? Well, the reason that works is because the numerator factorises as 1 minus t squared. And my denominator here is a difference of two squares. So, if you cancel one of the numerators with one of the denominators, all we get left with is 1 minus t over 1 plus t, exactly as required. So thankfully, nothing too tricky there. And then part B, believe it or not, is even easier. So let's just clear all this. We should actually expect this to probably be a bit harder, but it's not too bad. So this time we've got sin x. So if we write down our formula for sin x, what's that? Well, that is 2t over 1 plus t squared. So 1 minus this, so that's 1 minus 2t over 1 plus t squared divided by 1 plus this expression here. Right, so it's easier than it looks, and the way to do that is just to times both the numerator and the denominator by 1 plus t squared. So if we do that, what would I get? Well, this one here will be 1 times 1 plus t squared, so I just get 1 plus t squared, and with minus 2t. Same with the denominator, we just add 2t. So that actually just looks like this. T squared plus 1 minus 2t. Same again in the denominator, we get t squared plus 1 plus 2t this time. Okay. Now, I've kind of done this in a funny order. It might help if I write in the correct order. So this is t squared minus 2t plus 1 divided by t squared plus 2t plus 1. And at this stage here, hopefully it's clear to see what these two factorise as. So my numerator, that's just what we had previously. That's 1 minus t squared. The denominator is 1 plus t squared. So we could write this as 1 minus t divided by 1 plus t all squared. Oops, what's going on? That's all squared. So, if you notice, this is the expression we had in part A. So this is sec x minus tan x. And if we square the full thing, that is just sec x minus tan x all squared. So this is equal to sec x all squared is equal to this expression here. Okay, so there we have it. So that brings us to the very end of this video. So I hope this has helped. I think this actually worked out to be quite longer than I expected it to be, but I hope it's been a helpful video.